Here, entire cavity is filled with copper water nanofluid saturated porous media, and in an externally imposed magnetic field of string V0 is imposed on the entire cavity. And boundary condition, the side hot walls no slip and theta equal to 1, side moving wall, upper direction is moving, and gradient, temperature gradient equal to 0. Bottom wall is also adiabatic with temperature gradient 0, no slip. Top wall, it is the cold, theta equal to 0. And geometry of the wall is defined by the xy coordinate. And mathematical modeling, the governing non-dimensional form equations that taken, first one is the continuity equation, and then two are the both x and y momentum equation, and this is the energy equation. That equation is used on the dimensionless variables in the length parameters, velocity parameters, temperature and pressure, pressure parameters, non-dimensional parameters, and the dimensionless parameters are the Reynolds number, Prandtl, etc., that can be defined in that way. And some assumptions are made during the analysis, that is the fluid may be taken as the steady, incompressible, laminar, Newtonian single-phase homogeneous condition, uniform spherical nanoparticles, local thermal equilibrium, BFTM model, shift structure, the uniform grids are chosen to.
Good morning to all of you. I am Professor Uttam Kumar Sarkar from Mechanical Engineering Department, Technomin Salt Lake. Today I am going to present my work on natural convection in a semicircular enclosure. So, internal free convection has been a topic of intensive research because it has ubiquitous presence in natural processes, engineering applications, biomedical systems, and so many other applications. Further, it presents an intricate coupling between the flow and transport processes, which often lead to a rich variety of flow patterns. There is an enormous pool of literature on the natural convection of different rectangular or square enclosure. In comparison to that, natural convection heat transfer on different non-rectangular enclosure is a relatively new subfield in the heat transfer research. It is to be noted that the enclosure with non-rectangular cross sections such as triangular or parallelogram section have several practical applications. Recently, Das et al. Reviewed the natural convection in different non-rectangular cross sections such as triangular section, trapezoidal section, or parallelogram section. With that, we come to the main motivation of this study, that is, after a detailed literature survey, it has been found that natural convection in a semicircular enclosure which is being heated from the bottom is not studied yet. It is to be highlighted that the analysis of natural convection is not a matter of course. It has important applications for the design of nuclear reactor, heat exchanger, electronic cooling system, etc. So the main objectives of the present study can be summarized as follows. The first one, to numerically analyze the natural convection phenomena in a semicircular cross-sectional enclosure which has an isothermally heated flat base and hydrothermally cooled semicircular top surface. Further, the study presents the effect of variation of Rayleigh number on the evolution of velocity and thermal field.
Hello everyone, I am Sujit Kumar from NIT Rourkela. Today I am presenting my first conference paper on the topic Computational Study of Flow and Heat Transfer Characteristic of Oblique Laminar Slot Jet Impingement on isothermally heated moving plate. Now in this presentation, I will discuss the following section: introduction, problem specification and methodology, validation of present work, result and discussion, conclusion and references. Let's come to the brief introduction of the impeachment jet cooling. The impeachment method is one of the efficient methods for cooling of a heated item, heat treatment of the metallic product, tempering of glass, drying textile and food stuff. It also enhances the cooling of efficiency in the electronic industries nowadays. The cooling depends upon the geometrical condition of impeachment jets. The flow and heat transfer characteristic of multi-jets can highly differ from a single jet. The main objective of the research is to study of flow pattern and thermal characteristic of laminar twin oblique jet impingement over a moving flat plate, and also to perform the parametric study by varying the following parameters: Reynolds number, velocity ratio, angle of impingement. Now, problem specification. The domain is restricted by two parallel plane surfaces as shown in figure 1. The lower surface is known as impinging surface, and the top confined wall holds the twin slot jet at some inclination with upper surface. The inlet velocity is uniform and the inlet temperature of jet is 300 Kelvin. The normalized dimension is used to define the geometry of the problem domain. The normalized width between upper and lower surface and normalized length between the innermost point of twin slot jet are H and L respectively. This is the schematic diagram of the domain. Here theta is the impingement angle from the upper surface, this is the inlet temperature, and plate velocity is infinity, and total span length is 60 dh. Dh is the normalized header diameter of the slot jet, W is the jet width, H is the normalized width between upper and lower surface, L is normalized length between innermost point of the twin slot jet, and 0.5 is the normalized hydraulic diameter of the slot jet. The following assumptions were taken while solving the computation. The flow is assumed to be laminar, incompressible, steady, and two-dimensional. The working fluid is air, and its thermophysical properties are assumed constant. The following non-dimensional governing equations are used to solve the problem. First one is continuity equation. It shows the conservation of mass. It means the rate of mass enter in the system is equal to the rate of mass leave the system. The second equation shows the momentum equation in x direction and the third in y direction. The fourth equation shows the conservation of energy. In the above equation, there are many non-dimensional variables are used, which are following: x, y, u, v, p, etc. The velocity ratio. It is the dimensionless parameter defined by the ratio of plate velocity and jet velocity. In this study, the value of velocity ratio is considered in range r is equal to 0 to 2.0. Mathematically, it's given in equation 5, and the local Nusselt number is obtained by the following equation: Nux is equal to minus d5 by dy in equation 6. And now move to the boundary condition. No slip boundary condition are imposed on the walls. The top wall, which contains the impingement jet, considered as adiabatic. The impingement plate is considered as isothermal and moving with velocity infinity. Both sides of wall flow boundary imposed by constant pressure outlet. The computation of various combinations of parameters were performed by taking one parameter as a variable, while others were keeping constant. The combination of parameters was tabulated. The total 75 combinations were computed and results were observed. Now come to the solution methodology. The solution was performed in ANSYS 18.2. An algorithm was selected, PSOAM, in which momentum and energy discretization scheme power law were selected. The residual was set 10 to the power minus 6 for all cases. Grid independent tests were performed for the different combination of a grid a stationary plate. Four refinement levels were selected for the grid independent test. For all cases of refinement, the variation of local Nusselt number curve along its axial length are computed and plotted in figure 4. And peak value of local Nusselt number and average Nusselt number are tabulated in table 1. It can be seen that beyond the third refinement, 74 into 250, the change in Nusselt number distribution is insignificantly. So the grid size 74 into 250 is selected for the present study. And the figure 3 shows the sample base used in the computation of the flow domain of full domain. Now validation of present work. The strategy is followed to solve the problem include the validation of numerical solution for the twin slot Z impingement. In this, the result were obtained from the given parameter, Reynolds number 100, L is equal to 4, H is equal to 8 at different angle at theta, compared with the result of series for a stationary plate condition as shown in figure 5. Overall good match has been obtained. Now comes in result and discussion section. First we discuss a streamline pattern. Figure 6 and 7 show the streamline pattern for a stationary plate at Reynolds number 100. It can be seen for a stationary plate condition. The symmetric flow field is obtained when the impinging jet divided into two walls. The formation of multiple recirculation occur. Figure Figure 8 to 13 represent the streamline pattern for for moving plate condition at different Reynolds number and different velocity ratio, and also at different theta impingement angle theta, in which the streamline pattern different for different velocity ratio, and different for different Reynolds number. It can be seen that multiple recirculation uh, are occur in left side region. Now comes to the temperature contour. It For a stationary plate condition, symmetrical pattern of temperature distribution is observed as shown in figure. The region surrounded the jet interest has significantly lower temperature, which indicate the existence of recirculation region. Temperature of the domain is more uniform at the case of lower impingement angle. For a moving plate condition, it also seen that the temperature distribution is different at different location, and the at lower impingement angle, the distribution temperature distribution is more uniform in this. Now comes to the Nusselt number distribution along plate length. Figure 20 shows the distribution of local Nusselt number along plate length. It can be seen that at high value of impingement angle, more localized cooling at jet region occurred. At lower impingement angle, more distribution cooling occur, and the curve at an angle 45 is higher than all cases. Hence, for more distributed cooling for a stationary plate condition, impingement angle 45 prefer. And the figure 21 shows the one of the combination of moving plate condition in which impingement angle is taken as a variable. The overshoot in local Nusselt number near the left region is due to pressure outlet boundary condition and negligible a small boundary thickness. And figure 20 shows the Nusselt number distribution for various velocity ratio at constant impingement angle and constant Reynolds number. And it can be seen that higher velocity ratio, high value of heat transfer occur, and it more uniform. Figure 23 shows the variation of local Nusselt number for a various Reynolds number. While other parameters are kept constant, it observed that the value of local Nusselt number increases when increase the Reynolds number. Hence, heat transfer increases with increased Reynolds number. And figure 4 shows the comparison a study of average Nusselt number for a different Reynolds number at different impingement angle. It can be seen that when Reynolds number increases, the average Nusselt number increases too, and more heat transfer occur at greater impingement angle. Conclusion: for a stationary plate, a symmetric pattern of temperature distribution and a streamline are observed. For a more uniform cooling, the value of theta should be in between 30 to 55. At higher value of Reynolds number, the peak value of NU is shifted toward the jet region. As the Reynolds number of the jet increases, there is increase in the value of Nusselt number. This trend even followed when the velocity of the plate increases. For the range velocity ratio, consider the study with increase the plate velocity, the value of Nusselt number jet inlet region decreases. The value of Nusselt number increases with increase the Reynolds number for the given value of impingement angle. The highest value of average Nusselt number for a given Reynolds number is observed when the impingement angle set 90. And these, these are references. And thank you.
Good morning. My name is Ansh Patel and I'm an undergraduate student at VJTI Mumbai. Today, I'll be presenting the research done by me and my fellow classmates under Dr. Mandar Tendulkar at VJTI. The title of our paper is Performance Enhancement Analysis of Diffuser Augmented Wind Turbine Duct. We'll start with a brief introduction to the topic. Since large wind turbines are difficult to install in populous cities, modular wind turbines are becoming more and more suitable for small-scale power generation. The diffuser augmented wind turbine is one type of such a small scale turbine. As it is surrounded by a duct, it can produce up to twice the power of a bare turbine. This is because the duct helps accelerate the incoming wind, which increases the power output. The duct also helps reduce the aeroacoustic noise generated by the blades, which is another issue in populous cities. The aim of our project is to enhance the performance of the duct of a previously designed diffuser augmented wind turbine. This is achieved by integrating two aerodynamic devices, namely the vortex generating flange and the flow deflector. We have used the ANSYS Fluent software to gauge the effects of these improvements. We have selected a previously designed diffuser augmented wind turbine as a baseline model. It was designed by the alumni of our college as part of their undergraduate thesis. This thesis can be found from reference number 4. So the operating principle of the flow deflector is that it is placed in the upstream region of the turbine and it diverts the incoming wind to the outer regions of the blade. Due to the continuity equation, the decrease in flow area that results from such a diversion increases the velocity of the incoming wind. Thus, the lift force, torque, and power output of the turbine increase commensurately. Moving on to the vortex generator, it is the flange on the outer surface of the duct. Due to its blunt shape, it causes flow to stagnate in front while a wake is created in the downstream region. This causes vortices to shed from both the internal and external forces. The lower pressure wake is spread over the outlet plane of the diffuser, creating a lower pressure outlet. This will accelerate the incoming wind and hence increase the turbine power output. I will now talk about the computational modeling. We carried out flow simulation on ANSYS Fluent from which the throat velocity was computed. This parameter was used to select the optimal configuration of the two devices. We simulated two-dimensional turbulent flow at steady state using the K-omega model. This model was selected as it has become the industrial standard for external flows. We used the pseudo-transient solver settings as the under-relaxation of the method allowed convergence for all cases. We used a rectangular flow domain of length 31.5 meters and height 10.5 meters. The mesh settings were as shown in the slide. To obtain convergence, we decrease the mesh size for subsequent iterations. In this slide, the boundary conditions are shown. The incoming wind speed is the yearly average speed in Mumbai. The governing equations solved by the software are the continuity equation and the Navier-Stokes equation. We began by optimizing the flow deflector geometry. First, we selected the optimal overall shape. We considered a flat plate, a solid body with slots, a NACA 0012 F-oil, and an F-oil rotated by 180 degrees with respect to the flow. A decision on the optimal geometry could be made by considering the average velocity in the concentrated region, shown by these yellow lines. As we can see in the table, NACA 0012 airfoil rotated by 180 degrees gave the highest increase in VCONC over the baseline model. Hence, it was selected for further analysis. The solid body performed poorly as it caused significant wake formation. The NACA 0012 airfoil, due to its aerodynamic shape, had minimal separation and hence gave the best results. Now we look at the optimization of the flow angle of the airfoil. This is the angle between the wind velocity.
Good morning to everyone present here. I am Jashwant Themas, co-author of the paper, A New Efficient Flux Limited Scheme for Only Euler Equations. We are grateful to FMFP and IIT Guwahati for giving us an opportunity to present our work here.
The objective of our work is to create a hybrid scheme that incorporates the advantages of the parent schemes it is based on. We have compared the result of this hybrid scheme with its parent schemes for standard one-dimensional test cases involving shocks and uncertainties. The hybrid scheme is observed to perform better in handling numerical anomalies such as overshoots, undershoots, wiggles, and also demonstrates better shock capturing abilities. The parent schemes which we have chosen are the Lax-Friedrich scheme and the Lax-Konrad scheme. The conservative form of the two schemes are shown in this slide, and we have used the Richter-Meyer method for Lax-Konrad scheme. Here, U is the conservative, F is the flux vector, and lambda is equal to delta T by delta X. The reason for choosing these schemes are that the Lax-Friedrich scheme is an explicit first-order accurate scheme, so the results of the Lax-Friedrich scheme may not be accurate because of the diffusion, but the solution has no spurious oscillations. The Lax-Winthrop scheme is a second-order accurate scheme, therefore the solution is more accurate, but it has spurious oscillations at the discontinuities and corners. As mentioned, the objective is to develop a hybrid scheme that has an improved accuracy comparable to the second order scheme, but without the spurious oscillations typical to a second order scheme. We have used standard Sawtooth test cases for validating our results. Totally, we have used 3 test cases for validation. The first 2 test cases are standard Sawtooth cases which we have taken from the paper published by SWOT. The first test case, the shock tube is 20 meter long and it is divided into 2 equal sections. The working section and the driving section. Pressure and densities as mentioned in the table. The interaction between the two is studied after the partition is removed. The second test case is similar to the first test case, but the length is now 25 meters and the sections are divided as 10 meter long section and a 15 meter long section. The pressure ratio between the left and right sections is now 100:1 and density ratio is also now 100:1 compared to 8:1 density ratio in the test case 1. Test case 3 is a blast wave problem and we took the test case from a paper published by Woodward and Colella. In this test case, the shock tube is divided into 3 different sections as shown in the slide and the properties are as mentioned in the table. The distinction of this test case among the 3 is that there are multiple interactions of shock waves and contact discontinuities which are captured in the results. Unlike the other 2 test cases, the interaction of strong shock waves and discontinuities were not captured well with the coarse grids. Therefore, we had to use a finer mesh in order to capture the results better. The hybrid scheme, as mentioned, is a combination of Lax-Friedrich scheme and the Lax-Winthrop scheme. The Lax-Friedrich scheme is modified before using it in the hybrid scheme. This is done in order to reduce the step oscillations produced in the results. This is achieved by introducing the artificial viscosity in the conservative form of the equation, and the result produced was smooth without any oscillations. The epsilon in the original equation is changed into a weighted average function in order to introduce the artificial viscosity. In the weighted average function, the variable A is the fluid velocity at the node I plus half, and theta is the weightage factor such that the value of theta lies between 0 and 1, and it is determined by trial and error method. The Lax-Winthrop scheme is used as it is without any modification. The conservative form of the hybrid scheme is given in the slide. The parent schemes are incorporated in the flux term of the equation. The flux in the hybrid scheme has a character phi which ensures that the scheme doesn't produce Fourier oscillations. The function phi used is taken from a paper published by Zalesek on multidimensional flux character transport algorithms. After using the phi from the paper, the character term turns out as a min-mod function of 3 variables. Here, the flux terms with superfix 2 and 1 are conservative fluxes of the second order Lax-Wendorf scheme and the first order Lax-Friedrich scheme respectively. So the flux term of the hybrid scheme turns out as shown in the slide. At corners where there is spurious oscillations in the second order scheme, the min-mod function turns the flux character into 0, thereby making the flux of the hybrid scheme fully dependent on the modified Lax-Friedrich scheme. So there will be no spurious oscillations. At rest of the places, the equation is a combination of modified Lax-Friedrichs and Lax-Wendorf schemes. The value of theta and mu are found out using the trial and error method. And the value chosen is such that it works in all 3 test cases. The codes for all these schemes are written in C++. The following slides contains the results of all 3 test cases, and the graph in the top left corner is a pressure graph, and the graph in the lower right corner is a velocity graph. So for test case 1, we can see that the Lax-Friedrich scheme is less accurate and the Lax-Wendorf scheme has some spurious oscillations at the corners and discontinuities. But the hybrid scheme incorporates the advantages of both schemes appropriately. And for the test case 1, the CFL value is 0.2, nu value is 0.3 and theta value is 0.5. Similarly, for test case 2, we can infer the same points, but the test case 2 has a CFL value of 0.1. From the results, we can see that the flux limiter works as intended and the hybrid scheme does not produce any spurious oscillations. Also, it maintains the accuracy of the second order scheme. In the test case 3, the oscillatory Lax-Wendorf scheme produced fluctuating results and therefore was not plotted for comparison. But the hybrid scheme was more accurate than the Lax-Friedrich scheme and the Lax-Wendorf scheme. And the CFL value for test case 3 was 0.2 and the nu and theta value remained same for all 3 test cases. In conclusion, the hybrid scheme is able to produce accurate results without spikes or oscillations. When compared with the Lax-Friedrich scheme, it is less diffusive and therefore more accurate. However, the addition of artificial viscosity makes the scheme diffusive at the discontinuities and shocks, thereby reducing the accuracy at those particular places alone. But it is still more accurate than the spurious second order Lax-Wendorf scheme. The advantage of this scheme is that for different test cases and different scenarios, the 2 parent schemes can be combined appropriately with the variable theta as the handle. And similar to theta, the mu can be used as a handle for adjusting the artificial viscosity. When compared with more sophisticated schemes like row solvers, the hybrid scheme has a comparable accuracy and can be developed into a multi-dimensional scheme. Once again, we thank you for this opportunity.
Greetings to everyone. My name is Vinod Kumar Saini and I am here to present numerical study of ineffectiveness and inefficiency of air-cooled condenser under the guidance of Dr. Hardik Kotadia, Department of Mechanical Engineering, IIT Jodhpur.
But anyway, we are not going to change that.
This is the outline of the presentation.
So I think everything is fine. So nothing that script video.
Heat transfer is widely used in almost every type of industry to remove the heat from the machinery parts.
Okay.
Heat can be transferred between 2 different temperature fluids via direct contact in between them or without direct contact in between them. But most of the application in industry require no direct contact between both the mediums. like in the condenser, where both like one fluid flow inside the tube bundles and the another fluid flow at different temperature outside the tube bundles. And in the whole process, heat is transferred via surface of the geometry. So if we will increase the surface area of the geometry, the rate of heat transfer will be increased, but it will restrict the flow of the fluid. Heat transfer was always a topic of interest from the early times, and many techniques were found for enhancement of heat transfer. Huffman et al. Studied the effect of thin geometry and thin dimensions on heat transfer and pressure drop. Yuldich and Yunchu experimentally investigated reconvection characteristic on another fins on a horizontal cylinder. Liu et al. Performed numerical investigations to determine the airside performance of heat exchanger. Hossein Nemati performed numerical simulation for different turbulent model on fin tube heat exchanger. Lane et al. Studied the air side thermal performance and overall cycle efficiency for different type of air-cooled condenser.
All those things you just remove or keep it there, and that these tables should be very clean, and only these.
The objective of present study is to study the enhancement of heat transfer coefficient in the air-cooled condenser and compare the performance of the air-cooled condenser after the enhancement and observe the behavior of heat transfer and the performance of air-cooled condenser with the mass flow rate. These are the geometrical parameters of air-cooled condenser, in which stainless steel 30 mm inner diameter pipe are used with the pipe thickness of 2.5 mm, and thin inner diameter was 35 mm and outer diameter is 70 mm, and fin was used tapered. So the fin tip thickness was 0.15 mm and fin root thickness at the surface of the pipe was taken 30 mm, 0.30 mm, and the fin pitch is taken 2.3 mm. And here we can see this is the inlet of the air in the direction of flow. The pipe longitudinal pitch was taken 67, and in the transverse direction of the flow, the transverse pitch is taken at 77 mm. And there are 3 row of tube bundles is taken, and number of tube in each row was 13, 14 and 13. And for the original view, we can see the 3D model, which is the complete view of the air-cooled condenser.
These are come, then you will show in how.
There are many different models available in the ANSYS fluent, but K omega shear stress transport model was used for the study because it is mostly used for best predictable model in this field, and it gives the close approximation of flow separation near the wall for y plus less than 1, and for analysis unstructural mesh was used, and mesh was performed fine near the wall to observe the separation phenomena, and grid size was selected such that the y plus should be less than 1 near the wall. Result of the simulation in the ANSYS converges with the mesh size. So over results should be independent of the mesh size. But increasing the number of elements will also increase the simulation time. So to find the optimum grid size, mesh independent test was performed from coarse to fine mesh, and at 3.7 lakh number of elements, it was found that there are no much changes in the results. Boundary condition at inlet was given as air inlet velocity, and temperature of air was given as 298 at room temperature, and the boundary condition at pipe hole was given no slip condition, and pipe inner wall temperature was given as 318 Kelvin, which is close approximation of 95 millibar steam pressure. And at outflow condition was given, and to reduce the simulation time, symmetrical condition was given in the axial direction of the pipe. To validate the turbulence model, the numerical simulation was performed without thin tube bundles with K omega models, and the result of the simulation was compared with the formula given by Dukaskas, which is depend on Prandtl number and Reynolds number. For a range of 2000 to 11,000 Reynolds number, the Nusselt number and was calculated for Dukaskas formula and from the simulation also, and the error in between two was around 2.5 to 5%, which is in acceptable range. And this is the graphical representation of Nusselt number with the Reynolds number for calculated and simulated cases. Heat transfer rate was calculated by m dot Cp delta T, in which m dot is the mass flow rate of air at inlet, and Cp is the specific heat of air, and delta T is the temperature difference of outlet and inlet of the air. In the first table, the heat transfer without thin tube bundle was calculated, and this is the temperature difference for the given mass flow rate of the air, and corresponding heat transfer rate was calculated. After that, for same mass flow rate of inlet air, the temperature difference for actual and ideal case was calculated. In the actual case, the pipe inlet temperature is given, and the thin surface temperature will vary according to the conduction. And for ideal case, the thin surface temperature is given same as the pipe temperature. So in this case, the ideal heat transfer rate will be found, and from both the data we will calculate the fin efficiency and fin effectiveness. Heat transfer rate is calculated with fins and without fin cases for a range of mass flow rate, and it was found that rate of heat transfer increases with the increase in the mass flow rate, and fin effectiveness is the ratio of heat transfer rate with fin and heat transfer rate without fin, and fin efficiency is the actual heat transfer rate to the maximum heat transfer rate can be possible. So for this range of mass flow rate, the fin effectiveness was found with the range of 7 to 10.8, and fin efficiency was calculated around 98 to 91%. And this is the temperature control comparison and pressure control comparison with the thin and with thin cases. And here in the temperature distribution, we can see that the temperature changes around average temperature changes 3 to 4 degrees centigrade, and here is around 16 degrees centigrade inlet and outlet temperature difference. But for the same case, here is the pressure drop is less, and with fin case it is more pressure drop in the inlet to outlet case. The whole study shows the numerical analysis of air-cooled condenser with fin and without fin cases, and fin efficiency and fin effectiveness was calculated. And from the study we observed that fin effectiveness is maximum for higher mass flow rate, and fin efficiency is maximum for lower mass flow rate, and it decreases with increasing in the mass flow rate. And for air volume flow rate of 4,890 meter cube per hour to 18,335 meter cube per hour, fin effectiveness lie between 7 to 10.8, and fin efficiency for the same volume flow rate lie between 91 to 98.5, where 98.5 is fin efficiency is at lower mass flow rate.
Hello, greetings to all. My name is Shiva K. Battina, working with Professor Sudhir Siddhap Reddy from Indian Institute of Technology, Dharwad, India. Today, I am going to present a study on numerical assessments of thermal radiation from large kerosene open pool fires. The outline of the presentation is motivation and objective of the study, numerical simulations, semi-empirical modeling, resultant discussions, conclusions, and references. Motivation and objective of the study. Fire is the most common accident in process industries. Among all fire accidents, 44% of accidents are caused due to pool fires. The thermal radiation and convection contribution from such fires are 92 to 100% and 0 to 8% respectively. So it can be seen that thermal radiation is the primary source of open pool fire accidents. The experiment studies pertaining to measure the thermal radiation from a large open pool fire are limited in the literature. Moreover, conducting such big experiments are difficult, expensive, cause environmental degradation. However, few semi-empirical models are available to estimate the thermal radiation, but these models have its own limitations. Computational fluid dynamics studies have emerged as a promising tool to overcome these limitations. Using CFD as a tool, the thermal radiation from the fire source to the adjacent object can be assessed. So in this work, along with numerical simulation, semi-empirical modeling is also done, and results are compared with previously reported experimental data. Numerical simulations. In the present work, the numerical simulations are performed using Fire Dynamics Simulator version 6.7.0. FDS is a CFD code. It consists of large eddy simulations and direct numerical simulations. The present work is simulated using LES model, which offers less time demand than the DNS. Some of the major default features of the FDS are low Mach number LES, explicit second order energy conserving numeric, structured uniform grid, lumped species approach, diode of eddy viscosity closure, constant turbulence and Prandtl numbers, fast chemistry for single step reaction between fuel and oxidizer, gray gas radiation with finite volume solution to the RTE. RTE is radiative transport equation. Computational setup and boundary condition. Figure shows the typical computational domain having dimensions of 300 by 300 160 meter as width, length, height as dimensions. A uniform structure grid is applied in all the directions. The pool diameter considered in the present study are 30 and 50 meters. Mass loss rate per unit area is prescribed as a boundary condition, that is 0.063 kg per meter square second. All sides are set to open and the ground is set to inert. The soot yield and radiative fractions are considered at 0.042 kg per kg and 0.08 respectively. Radiative heat flux to the surrounding is measured by keeping the virtual radiative heat flux meters at a non-dimensional distance y by d equal to 1, 2, 3, and 4. These figures are taken from the present study. These figures show evolution of fire and smoke from the growth to steady state period with respect to time. Grid independency test. The resolution of the flow field of the fire depends on the number of grid cells that span the characteristic diameter d star. The grid resolution is expressed in non-dimensional form, that is R equal to d star by dx. The d star not only represents the impact of the grid size but also the fire size. From the figures, it can be seen that the estimated results show the reasonable accuracy for the range of R values 4 to 16 for the 30 and 50 meter pool phase respectively. Hence, in this study, R equal to 4 and 16 are considered for 30 and 50 meter pool phase respectively, as it offers relatively less simulation time and a reasonable accuracy in the results. Semi-empirical models. As I mentioned, in this work, semi-empirical modeling is also done to estimate the thermal radiation. So the applied models are point source model, Mudan model, Shokri-Baylor correlation, Shokri-Baylor detailed model. Coming to the point source model, this model assumes the flame as a single point source and the flame radiates the thermal energy from the geometric center of the flame equally. This model doesn't consider the atmospheric radiation and it overestimates the near field fire radiation since the geometry of the flame is not taken into account. This model predicts the far field intensity of radiation with reasonable accuracy. Shokri and Baylor correlation. Based on the large poolful experimental data, Shokri and Baylor proposed a simple correlation to calculate the radiative heat flux to an object located on the ground level at a distance of r from the center of the pool fire. The correlation is given in the equation. Coming to the next model, Mudan model. In this model, flame is assumed as a vertical or tilted, that is, radiation from the flame is with or without wind. This model also considers the impact of atmospheric transmittivity, configuration factor, along with effective emissive power. Shokri and Baylor detailed model. In this model, the flame is assumed as a cylindrical black homogeneous radiator with average emissive power. This model also considers the configuration factor between the flame and the receiving object. The configuration factor is the function of diameter of the pool, flame height, and target distance. Resultant discussions. The figure shows the comparison among the previous reported experimental results, numerical simulations, and semi-empirical model results of 30-meter kerosene pool fire. In the figure, x-axis, a non-dimensional distance y by d is shown. In the y-axis, incident heat flux to the surroundings is shown. From the figure, it can be seen that the simulated results are in good agreement with experimental results, and the simulated results are deviated 20% from the experimental results, and the deviation lies within the experimental uncertainty of 30%. Figure also shows the comparison of reported experimental results with semi-empirical models. Among these models, two are simplest and two are detailed models. Point source and Shokri and Baylor correlations are simplest models, and the detailed models are Mudan and Shokri and Baylor detailed model. Point source and Mudan models have better agreement with experimental results, and one more thing, except point source model, all other remaining semi-empirical models are overestimating the thermal radiation from the fire source. The estimation made by the point source model is better than the Mudan model. The deviation of point source and Mudan model from the experimental results are noticed as 0.6 to 19% and 1.3 to 58% respectively. The remaining two models, Shokri and Baylor experimental correlation and detailed models, are overpredicting the thermal radiation from 90 to 145% and 40 to 120% respectively. The reason for overestimation in Shokri and Baylor correlation is because of considering only the pool diameter and length between the source and target. While coming to the Shokri and Baylor detailed model, this model considers the flame as black and homogeneous radiator, but the majority of the radiation comes from the soot and it has a spectral dependency. Resultant discussions are continued. The figure shows the comparison among the previous reported experimental results, numerical simulations, and semi-empirical models results of 50-meter kerosene pool fire. It can be seen from the figure, the simulated results are slightly overpredicted at the near field of the fire, and the simulated far field radiation is well agreed with experimental data with the deviation of 8%. Coming to the semi-empirical model, for both the fire sizes 30 and 50-meter kerosene pool fire, point source model has given better estimation in thermal radiation from fire source. Conclusions. The present study assessed the thermal radiation from 30 and 50-meter open kerosene pool fires and compared the numerical results with various semi-empirical models and previous reported experimental data. The conclusions can be drawn from the present study are as follows. The deviation of simulated results of 30-meter pool fire is 20%, and the deviation lies within the experimental uncertainty of 30%. Coming to the 50-meter pool fire, the deviations at near and far field are 188% and 8% respectively. Coming to the semi-empirical models, among the various semi-empirical models, the point source model shows better agreement with experimental results. In summary, the simulated results are more accurate or semi-empirical models. These are the references cited for the present presentation. Thank you.
Dear professors and attendees, I am Frank Steve, and I would like to welcome you to the presentation, Interaction Effects of Radiation and Turbulent Natural Convection in Enclosures with Discrete Source and Sink. This work was carried out with the collaboration between Vellore Institute of Technology, Chennai, and Indira Gandhi Center for Atomic Research, Kalpakkam. Since my time is limited, let me go straight into the presentation. Contents of my presentation are the literature survey, followed by the problem definition, the objective, the model validation carried out, the work done, and the conclusions derived from the work, the future scope of this work, and the references. For my work, a vast literature survey has been carried out in order to define my problem statement, and from the detailed literature survey, it is concluded that no research has been carried out on the study of natural convection heat transfer in the turbulent regime for 3 source and 3 sink positions. The benchmark validation studies have been carried out in air medium by referring the Ampofo and the Carianis literature. From the detailed literature survey, the definition of my study is to investigate the interaction of surface radiation and turbulent natural convection in enclosures with different source and sink positions. As you can see in the figure, the source is considered on the left wall of the enclosure, while the sink on the right wall. The top, bottom, and the parts of side walls other than the source and sink are well insulated. The positions of the source and sink are equidistant between walls and to each other. The change in density with temperature is incorporated using the Bostonist approximation, and it is mentioned that only a pair of source and sink is considered per study, so you will get 9 possible combinations. The acceleration due to gravity is considered in the negative y direction in order to mimic the real conditions. Natural convection heat transfer and fluid flow in enclosures has been a subject of interest in many diverse fields of applications, namely building and thermal insulation systems, solar engineering applications, effective cooling of electronic components and machineries, and even in nuclear reactor cooling applications. So based on the current state of natural convection investigation, the knowledge gap lies in the calculation of heat transfer by natural convection, and hence the same has been done by me for multiple source sink arrangements in enclosures with involvement of surface radiation. Now it's important to understand how different turbulence models behave to different Prandtl number fluids. Hence, the sensitivity studies are carried out for different commercially available turbulence models and are validated against the available experimental benchmark literatures. Here, the 7 commercially available turbulence codes, namely the K epsilon standard, K epsilon RNG, K epsilon realizable, K omega standard, K omega BSL, the K omega SST, and the 1 equation Spalart-Almaraz model available in the Fluent software are compared for air, water, and liquid sodium. And these are the literatures that I have referred. Since my study mainly focuses on air as a medium inside the enclosure, I have presented only the results of air in the coming slides. The enclosure given by Ampofo et al. Literature is a square geometry consisting of air as the medium. The boundary conditions are employed according to the criteria of the literature as shown. A standard 100 by 100 quad mesh was generated for the geometry, and the computational grids are found to be clustered and staggered towards the walls. Here, the local Nusselt number along the horizontal walls is displayed. So the graph displays the experimental results with the dotted line, and these are the numerically generated values. It can clearly infer that the K epsilon models was able to predict a very good closeness compared to the K omega model and the Spalart-Almaraz model. So hence the K epsilon models can be preferred for these kind of problems. Furthermore, we can see from the next slide, the K epsilon standard model was able to predict the velocity field much more accurate as compared to the other models due to the least deviation from the experimental value. And also performing thorough grid sensitivity analysis, the K epsilon standard model was giving very good desirable results. Hence, the K epsilon standard model can be used for this study. Since my study mainly focuses on the turbulent region, 4 Rayleigh numbers of order 10 power 9 to 10 power 12 are chosen. The source is maintained isothermally at temperature of 343 Kelvin and the sink at 303 Kelvin. The 2D enclosures of length L and depth h are modeled with an aspect ratio of L by h 0.5, 1, 1.5 and 2. The depth h is varied accordingly in order to achieve the desired geometry. For the inclusion of surface radiation, 3 emissivity values, namely 0.3, 0.5 and 0.7 are taken. And since 3 sources and 3 sink positions are considered, a total of 9 possible combinations of source sink position